Today we look at the concept of mass moment of inertia, and we do it directly after the section on second moment of area. And the reason for that is there are similarities, but there are also major differences. So it's good to do the two fairly close to each other. Second moment of area, which we've just done, the units were meters to the fourth, and we were basically taking an area and multiplying it by the square of the distance from some axis. Now here the similarity is we are taking a quantity and multiplying it by the square of the distance from an axis. However, the quantity is now mass, not area. Next is to remember that A equals alpha r. Remember what A is. A is the linear acceleration of a body measured in meters per second squared. And alpha is the angular acceleration of a body measured in radians per second squared. And the tie-up between the two is radius. So if we look at a body, this blue depicted body over here, rotating about an axis over here with radius r, so it's going round and round in a circle. Let's make it clockwise in this case. At any instant, the linear acceleration of the blue body would be a, and at that same instant, the acceleration of this arm rotating about this point here would be alpha, and the tie-up between the two would be radius in the fashion shown over here. If we consider this blue mass rotating about that very same spot, and we also consider that rotation is occurring with increasing speed, in other words, there is alpha present. The radians per second, the angular velocity, is increasing with time. We have acceleration. Now remember that linear acceleration F equals ma, and remember that the angular motion, or the force causing it, relates to torque via this equation over here. So if we go back, we can get to a point where we end up with torque required for this angular acceleration to be m times radius squared times alpha. So the tangential force required to accelerate the blue object in its circular path would be its mass multiplied by the desired angular acceleration multiplied by the radius. At this point we can multiply both sides of the equation by radius. You'll see why in a moment. If we stand back and look at what we have here, mass times radius squared, which is present in this right hand part of the equation, is in fact known as this new quantity which we're starting to study today, which is known as the mass moment of inertia of the mass about the axis of rotation. Notice that it is mass times radius squared. Mass times radius squared. That is the quantity we're focusing on right now. Now we will seldom be analyzing a small spot of mass all by itself rotating about an axis. We'll rather be looking at different shaped rotating objects, such as a flywheel, for example, or a pulley or whatever. So if we're not looking just at one spot of mass, but a shape such as a flywheel, etc., what we could do is consider the millions of small pieces of that flywheel, each as its own little spot of mass. And then we focus on this equation over here, and we say, right, each little particle of mass, if we look at the FR product for it, and we look at the mr squared alpha component for each particle of mass, and we were to add them all together, we could get the equation for the whole shape. So we would have to take all the FR products of each and every particle of that flywheel, add them all together. Obviously there's going to be millions, and we would have to take, for the each and every same particle, we would have to take the mr squared alpha values for each particle, add them all together, and we would have the sum of all the FR terms and the sum of all the mr squared alpha terms. If we were to achieve that, the sum of all the FR terms would be the total applied torque on the wheel, and the sum of all the mr squared terms would be the total mass moment of inertia of the flywheel about its axis of rotation. Notice that alpha is still outside of that, suggesting that torque required for acceleration is the sum total of all the mass moment of inertia terms multiplied by this alpha. And if you look at what each term means in this simple formula, torque equals I alpha, this is the torque to accelerate the flywheel. I is this new quantity which we're learning about today, the mass moment of inertia. Notice its units are kilograms meters squared, and alpha is angular acceleration measured in radians per second squared. This is what we need to take forward from here. You'll recall from second moment of area we had this concept of radius of gyration, and it also applies here. I is mk squared. We can once again use this imaginary spot where we could pretend all the mass resided, and the distance to that spot would be known as k, and it is useful for calculations, as you're going to see. Here's an example to show how that would be used. If we have a flywheel and axle with a total mass of 160 kilograms and can be assumed to act at a radius of 250 millimeters, that means the radius of gyration. We can assume or pretend that the mass of 160 kilograms acts at 250 millimeters. We now apply a torque of 20 Newton meters. What's going to happen? Well, it's going to accelerate. There's going to be angular acceleration in radians per second squared. I is mk squared, we've just learnt. So the I value for this flywheel would be 10 kilogram meters squared. And we've just learnt the torque is I alpha. The torque required for acceleration is equal to the mass moment of inertia multiplied by the angular acceleration. So if we solve for alpha, under these conditions, if you were to apply the 20 Newton meters of torque, you would achieve 2 radians per second angular acceleration. Now here are some fundamentals of dynamics that we need to put in our toolbox to be able to continue. The equations of motion, which you have studied before, certainly in a linear fashion. V equals u plus at. Remember what the variables were. V is final velocity, u is initial velocity, a is acceleration, and t is time. V squared equals u squared plus 2as, s equals ut plus half at squared. You might have seen these with different variables at school, but this is the preferred way of using them from here onwards. Okay, so for each linear equation of motion, we can write an angular equation of motion. So the easy way to remember this is you memorize these, you write them down, and then you work out what the angular equivalent equation of motion is next to it. Let's start with this one. V is final linear velocity. In angular terms, we'll call that omega 2. Initial linear velocity we'll write as initial angular velocity as omega 1. Acceleration is alpha. T is obviously the same whether it is linear or angular. Same for the next two. Final velocity squared equals initial velocity squared plus 2as becomes omega 2 squared equals omega 1 squared plus 2 alpha theta. Theta is displacement, but in angular terms that will be how many radians you have turned through. So instead of displacement being in a straight line measured in meters, in angular terms displacement is rotation in radians. So to recap, in angular terms, velocities are given in radians per second, and we normally use the variable omega. Accelerations are given in radians per second or radians per second squared, normally use alpha. Displacement is now angular, how many radians one has turned through, that is our theta. Now angular velocity in engineering is often given in revs per minute. Okay, and that normally has the variable capital N. But we are using angular velocity in omega, which is radians per second at the moment. So we have to keep this little conversion formula in our toolboxes. Omega is 2 pi n over 60. That you just need to memorize. So whenever you need to convert between angular velocity in revs per minute to angular velocity in radians per second, you're going to use this formula here. And if you are ever given angular displacement in degrees and you need to give it in radians, remember that the conversion between degrees and radians is pi over 180. An easy way to remember whether you use pi over 180 or 180 over pi is remember that when you convert from degrees to radians, you need to make the number smaller. So you'll put the pi at the top and the 180 at the bottom, which will reduce your degrees and make it smaller into radians, because the radians number is always smaller than the degrees number. Here are a few examples. I suggest you stop the video and attempt each one on your own and then look at the solution. The first one is a rotating body has a radius of gyration of 600 millimeters, mass 200 kilograms. Calculate the braking torque. Now remember, the torque for acceleration and deceleration works in exactly the same fashion. We would just use a negative sign if it is deceleration. In this case, the braking torque, it will bring it to rest in 22 seconds from 210 revs per minute. So angular velocity is being expressed in revs per minute in this case. So initial angular velocity in radians per second, omega, is 2 pi n over 60, 22 radians per second. Pick the equation of motion that has all the variables in that you know and the one you desire. So it is omega 2 is omega 1 plus alpha t. Final velocity is 0. Remember, it came to rest, so that's omega 2. Initial angular velocity is 22 radians per second. And we are solving for alpha, the time being 22 seconds. So it turns out that alpha is negative 1 radians per second, or radians per second squared. I is mk squared. So there's your I value for this particular rotating body, 72 kilogram meters squared. And the torque required for acceleration is torque is I alpha. Torque applied was 72, in this case a braking or slowing down torque. Desired alpha is negative 1. So the torque you would need to achieve all of the above is 72 Newton meters of braking torque. Try this one next. A flywheel has a mass of 2,000 kilograms, radius of gyration 500 millimeters. What torque is required to slow the flywheel from 315 to 105 revs per minute in 40 seconds? Stop the video and try that one, and then restart once you have your solution in front of you. Initial velocity 315 revs per minute turns out to be 32.986 radians per second. That's initial angular velocity. Final angular velocity is 10.995. And remember that acceleration is always change in velocity over time. In this case, it's angular. So it is the difference in your angular velocity, which is final minus initial. So that would give you the change in angular velocity divided by how long it took, the time in other words. Turns out it's 0.54976 radians per second. So I is mk squared for this particular rotating body that you can work out separately. And to finish off, the torque required to achieve the desired angular acceleration, torque is I alpha, turns out to be 274.88 Newton meters. So in all the previous examples, we were given the radius of gyration of the rotating object. Hence, we were able to work out the I value. But what if we are not given that, and we have to, from first principles, work out the I value for a particular body? Well, let's start with the first one, which is an annular ring. First of all, what is an annular ring? Well, if you consider a cylindrical object rotating about the red axis, and you then make a hole through it, that would be an annular ring. So clearly this object has outer diameter, and it also has a hole with a certain diameter, and it also possesses thickness, which would be the distance across this way along the axis. That would be what an annular ring is in the context we are using now. So here's that very same annular ring looked at from this side, from a two-dimensional perspective. There is the outer circle, and there is the hole. Right, so what we're going to do is we're going to break up this annular ring into very thin slices. And those slices will be at a maximum radius of r and a minimum radius of r2. And each one will have a very, very small dimension del r. So there'll be a slice here and a million more all the way in, right the way to the center. So we're going to break up this annular ring into those elementary slices. Each one will have a thickness t. Now that is into the page or out of the page. Okay, remember it was this dimension here. So the volume of each elementary ring would be its length. If you were to cut the elementary ring and lay it out in a straight line, it would have length 2 pi r. Remember, that is the circumference of a circle. So 2 pi r would be how long each elementary ring is if it were laid out in a straight line. multiplied by its thickness, del r, and multiplied by the thickness into or out of the page. So that would be the cubic meters, the volume of each elementary ring. If we now multiply volume by density, remember we get mass, so now we're at kilograms. And if we were to look at the polar moment of inertia of each elementary ring, it would be all of the above multiplied by, remember, r squared. If we go back to the blue dot at the beginning, we took its mass multiplied by its distance squared to an axis, and we would get kilogram meters squared. So for each elementary ring, the mass moment of inertia would be 2 pi t rho r cubed del r. Now remember, we get to integration at this point because we're going to add up lots and lots, millions of little elementary rings. So the total mass moment of inertia of the disk would be all of the above, 2 pi t rho r cubed del r. We move all the constants to the left of the integration symbol, and we leave the variable, which is in the form r cubed, and we insert the limits that r is going to vary between. And remember, it goes from a maximum of r, which we'll call r1 now, to a minimum of r2. So make that an r1 on your drawing, and that is already an r2. So those are our limits. So we are integrating r cubed, which, as we know, becomes r to the 4 over 4. So the 4 can immediately slip to the left with all the other constants, and we're just left with r to the 4 inside the bracket with the limits clearly indicated over there. And remember, at this point, you then insert the one limit, insert the second limit, and put a minus sign between the two. And you are left with pi t rho over 2 once you simplify the constants, and in the bracket r1 to the 4 minus r2 to the 4. Remember from your maths, that is the difference of two squares, which can be written in this format over here. And then conveniently you have a look at all of this turns out to be mass. Let's think why that is. Pi t rho times r1 squared minus r2 squared. Now that would be the surface area of the annular ring multiplied by the thickness would be volume times density. Now remember, that is mass because mass is density times volume. So all of this, if you look carefully, is indeed mass. So you can replace it in the equation over here, replace all of that with mass, and you end up with I being mass times r1 squared plus r2 squared over 2. It's often easier to work with diameters rather than radii in engineering. And remember that diameter is simply 2 radii, or radii is diameter over 2, whichever way you prefer. So you can rewrite the above in diameters, and you end up with I is mass of the annular ring times brackets d1 squared plus d2 squared all over 8. If the annular ring is in fact a solid ring, in other words no hole in the middle, it's even simpler. I is md squared over 8. Now, to illustrate how we're going to use all of this, let's consider these two flywheels, which are identical in two respects. They both have identical mass, and they both have identical outer diameter. But in the first one, you're going to see that the mass is cleverly situated far from the axis of rotation. And in the second one, not so cleverly, you have a lot of the mass close to the axis of rotation. Okay, now the big difference here is the two flywheels would differ in terms of mass moment of inertia. Which one would have the higher mass moment of inertia, do you think? Well, flywheel A has much of its mass located far from the axis of rotation, hence it will have a larger value of I than flywheel B. And remember that a flywheel is used for storing energy. That's essentially the purpose of a flywheel. So for a given mass flywheel, you can achieve greater amounts of energy stored in this rotating object if you design it in this fashion rather than in this fashion. Now remember that I equals mk squared, and if I is md squared over 8 for a solid disk, then you can rearrange and find that k, radius of gyration, is in fact 0.3535d. You may or may not find that useful. And in a similar fashion, if it's an annular ring, remember that's a solid disk with a hole through the middle, I value is that, and I value is also mk squared, so k is all of that. So with all of that in mind, let's start with an example. We're going to determine the mass moment of inertia and radius of gyration about the axis of rotation, which would be through the center for a rotating object. That's fairly obvious in this case. The flywheel is manufactured from a material of density 7,000 kilograms per cubic meter. Okay, so what you're going to be doing here is you're going to break up the flywheel into known annular rings or solid discs, whichever is appropriate. In this case, it'll all be annular rings. So if we consider the outer portion as one annular ring, and we use the formula which has just been derived for mass moment of inertia, and then we consider this annular ring here, and we add the two together, we should get the answer. So at this point, stop the video and attempt it yourself, and then look at the solution only once you have made a good attempt at it. Start by working out the volume of your first annular ring, and remember that volume is outside area times thickness, and then mass is density times that volume you just worked out. So it turns out that piece 1, which is defined here, which is this outer one, has a mass of 15 and a bit kilograms. And we've just learnt a few moments ago that I is m d1 squared plus d2 squared over 8. So we plug that in and we find that ring 1 has a mass moment of inertia of 0.288 kilogram meters squared. In the same fashion, ring 2, the inner piece over here, has a mass of 8.24 kilograms and a mass moment of inertia of that much in kilogram meters squared. Now you may add up both because they are both about the same axis of rotation, 0.355 kilogram meters squared. Finally, to find the radius of gyration, I is mk squared, remember? So I you've just worked out. Total mass, by the way, you need to add up the two, and you find that radius of gyration of this entire flywheel, that imaginary point where you could consider or pretend all the mass to act such that you had the same mass moment of inertia, would be 123 millimeters from the axis. It'll be out here somewhere, will be that imaginary spot. Quite useful when we calculate, as you'll see. Here's a very similar example, which I'd like you to try at this point. You can stop the video and attempt this one yourself. I suggest you take it from beginning to end and only then restart the video and look at the solution. As before, we find the mass of each piece, and we've broken it up into two pieces. The annular ring with OD, outside diameter 1000, ID 200 and thickness 140. That's piece 1. And then piece 2, each has these masses over here. So the total mass of the whole rotating object is 1953.93 kilograms. The I of each piece is worked out in the same fashion as the last example, 97 and 102 kilogram meters squared. They may be added because they are both about a common axis. And you can then find radius of gyration of this entire rotating object at 319.7 millimeters. Then you were asked to find the time it would take to accelerate the wheel from this angular speed to that angular speed, and the torque of 23 Newton meters was applied constantly throughout that process. So back to torque is I alpha. Remember that was the torque required to accelerate an object, was torque equals I alpha. So we work out that the alpha, the angular acceleration we're dealing with here, is 0.1151 radians per second squared. And this angular acceleration is final angular velocity minus initial angular velocity over time. So the time that it will take for this to happen will be 727.85 seconds, which is 12.13 minutes. Incidentally, this very object that you just worked with, you could draw it in CAD, and you could ask the CAD system to give you the mass moment of inertia, which is in this printout over here. Now, what if you have a wheel that has spokes in it? It could be a bicycle wheel, it could be a flywheel with spokes, it could be a type of wagon wheel. What if we have to consider the mass moment of inertia of this whole affair? And what we've learned so far is we can deal with this inner portion and the outer portion quite easily with the formula we've just learned. But what about these spokes? They're also going to have some effect on the mass moment of inertia of the whole wheel. So let's look at that next. Let's consider each spoke as a thin or slender rod. And let's start by working out the mass moment of inertia about an axis passing through the center of gravity. That's here. Once again, let's break up the object into thin slices. Del x would be the thickness of that slice, and we'll make each slice distance x from the axis in question. And remember, the full length of the spoke or the thin rod is L, so we'll make it L over 2 the one way from the center of gravity and L over 2 the other direction. So the cross-sectional area of the rod, we'll make A, that would have units meters squared. Density will be rho in kilograms per cubic meter, and M will be the mass of the complete rod. So mass of each element would be its density times its cross-sectional area times that very thin thickness it had of del x. So IgG, that would be the mass moment of inertia about axis GG, would be rho A del x, which was mass, multiplied by, remember what we do, we multiply by distance to the axis squared, which is in our case x for this little elementary piece. X squared would then be that squared. So IgG of the complete rod would be the sum of all of that using integration. We have rho A del x, x squared, and we have limits L over 2 and minus L over 2. As before, take the constants out, which would be rho and A, leave only x squared dx on the right hand side, and we would then turn x squared into x cubed over 3, and as before, the 3 can go to the constants, and we are left with simply x cubed in the bracket. Apply the one limit, apply the other limit, and we have a minus minus, which gives us the plus over there. And then we step back and note that rho A times L is in fact mass. Let's think why that is. Area times length would be the volume, times density would in fact be mass. So we remove one rho AL term out of the equation and we replace it with mass, and we are left with L squared and 12. So IgG of a thin rod about an axis passing through its center of gravity is mL squared over 12. But we're not particularly interested about the mass moment of inertia about an axis passing through its center of gravity. One end would be more useful. So cast your minds back to parallel axis theorem. I about a new axis is equal to I about an axis through the center of gravity. Remember, it had to be a center of gravity term here. Plus m times the distance to this distant axis squared, which in our case is now L over 2 from the GG to the end. And you find that I about an axis passing through YY would in fact turn out to be mL squared over 3. Have a look through that one. And of course you could apply the same principle to go to an axis not just through the one end, it could be an axis even further away. For example, the center of rotation of the flywheel or whatever. As long as you start from a GG, you can go as far as you like. It need not be L over 2, it could be further. Here's another example, not directly related to what we've just done, but I suggest you note down this example, stop the video and attempt it, and then restart the video once you've made a good attempt at it. Here's the solution to that one. I'm not going to go through every step because it is exactly like before, but basically one worked out the mass of each piece, got the total mass, worked out the I of each piece, added it up, and then looked at torque equals I alpha to find the angular acceleration that resulted, and finally worked out the time for that acceleration to occur using some of the tools from our toolbox or our summary sheet, our formula summary sheet. Okay, so work through that solution. Right, here's our final example for this little section of work, and here we get to use the spoked formula, or the formula for spokes that we spoke of earlier. So we have a spoked flywheel. Determine the mass, moment of inertia, and radius of gyration about the axis of rotation, and the density is given. Okay, so we have an outer rim, we have a slightly smaller inner rim, we have 8 spokes, 1, 2, 3, 4, 5, all the way around to 8, and we have a center boss. So there are distinct areas or pieces. The outer ring, the slightly smaller ring, that's 2, the spokes, there are 8 of those, and the boss in the middle. Okay, so as before, stop the video and make a good attempt at that. This is our last problem, so make sure you get that right. And I've made a little note to myself here, rather work in diameters. So the solution I'm going to show you works in radii, as I recall, but you can work in diameters, that's fine. There's piece 1, check your answer there. Piece 2, piece 3, piece 3 being the spoke, converted using parallel axis theorem to the center of rotation. So for each spoke, you have 0.03476 kilogram meters squared. Remember, that'll get multiplied by 8. And finally, you need to get this total, 14.485 kilogram meters squared. The very last step, I equals mk squared. So k is 312.5 millimeters. That would be the spot where you could pretend all the mass of the flywheel to exist to achieve the same I, 312.5 millimeters.